Okay, I guess we can go ahead and start. It's 2:49. I have graded your exams, but I left them at home. I forgot to bring them to campus. But I have your equation sheets right here. If you want them back for your records or for the final, you can just take them. They're right in front of the class. And I have not uploaded the grades on Blackboard, as you, I assume, have noticed. The reason is I was a little disappointed with the grades. I mean, we have a lot of people who got good grades, but I was expecting more people to get better grades because in my mind, this was a very fairly easy exam. Okay? So I think there is a disconnect here. So either you guys are not following me or I'm not doing a good job teaching you the material or something is happening, okay? So we need to talk about this a little bit and then decide on what we want to do for this first exam. Because at the end of the day, my goal here is not to fail you or to torture you or like, I received an email, forget what, but a lot of people were stressed about this exam. I don't want you to feel stressed. I mean, a little bit of stress is not bad because it can be motivating, just a little bit though, not too much. And so, yeah, I want to hear from you to see what the problem is, even if we need to spend all of this class on how to make sure you all are learning the material better, right? I don't want to dumb the class down just to make it easy for everyone. I want to teach you as much as possible, right? And I want to help you understand those like complex topics because you are all smart enough to understand those, right? I'm pretty sure all of you are smart enough. And yeah, so help me solve the disconnect, right? And I talked to one of your classmates after the class, after the exam the other day, and what he told me was that you are used to the type of exam that your professor gives you the equation sheet or the equations you need to use for a specific problem, and that just to apply and try get the final answer, which is not what we are going to do. Definitely, this is not what we are going to do in this class, and it is not definitely what you are going to face in the real world, right? In the industry, if you are faced with a problem, you have the tools, like the equation sheet, right? You can go back and Google and whatever, but you have to find the appropriate tool for the problem, right? I cannot tell you that this is the tool you need to use. Your boss is not going to tell you they're paying you like $100,000 a year to figure that out, right? To find that link, to find that appropriate tool, right? So one of the skills you need to learn in college in general is that a specific skill, to find the appropriate tools to solve a problem, right? I mean, some of the problems you're going to face are not going to be mathematical problems, but finding the appropriate tool is one of the skills you need to learn. So that's definitely what I'm not going to do. I'm not going to give you an equation sheet or tell you what equation to use for what problem. And honestly, in my mind, that's a waste of your money. You are the ones who are paying for this class. Even if you are on a scholarship, you will pay it with your future tax dollars. Yeah? Scholarships come from your tax, all of our taxes, right? So you will definitely pay for it in a way. And yeah, so let's talk about it. Let's figure out the problem. Let's figure out the disconnect. And again, my goal is for you to learn. My dream is for all of you to get an A out of this course. It is definitely not possible. I didn't get an A out of my fluid mechanics. It is a tough course. I don't expect all of you to get an A, but I want all of you to learn. Right? Go out of this course and like think with yourself that I really learned something. Okay. So yeah, let's talk. And this, I mean, if you are not very comfortable with talking, and I understand that, which is true with most of your junior level students, right? Most of your junior. This is sophomore? Okay. That's even worse. Like sophomore level students are less comfortable with talking, right? And I understand that, but you have to start becoming comfortable. So maybe give yourselves a little bit of discomfort, start talking, tell me what the problem is, and then we'll go from there.
Honestly,
Yes.
for me, I wasn't like ready for all of the terms on the exam. Like I thought it was gonna be just more like you had like the understanding of it. I just didn't like the Pascal's law thing. I just didn't write down like the term. Like I forgot what it's like equation stuff. Like went with it.
Okay.
So
Okay.
that kind of like hurt me on the exam a little bit.
Yeah. That's okay. Okay. I understand that part. So, yeah. I guess that was the experience for the next exam. Like you just have to make sure you understand all of the laws, all of the concepts, and all those things, right? Because yeah. Yes.
One thing that I think that students that said about the equation sheet, I'm not in none of my classes. It's like per question. I've never had a class that was like this is the equation you should use because I feel like that's just them telling you what to do. But in all of my other classes, Yara provided the equation sheet of just all of them.
Okay.
Like exactly what we made, but at least I know that like when I was making it, there were some things I saw from like our PowerPoints or whatever that like I kind of just had to guess on what I thought should be on there when like usually we're just provided, so it's kind of hard to do it out myself. And it's like I don't know what materials is going to be on the test. And like if that's the point, that's the challenging part. But then if we're given an equation sheet, I feel like it's more productive to just have the ones we need, not necessarily knowing what questions to go with.
Okay. I understand that, and that's one thing that I'm kind of against. So I don't want to provide any type of equation sheet for you, right? The class itself is an equation sheet. I have to teach you the material. And if you don't have the perspective to understand which equation is the more important one, that's where the disconnect is, right? That's what I want to solve. Right? Well, at the end of the day, I want you to look at the lecture notes and understand that this part is a very important part. Like the Bernoulli's is important. Like I was very surprised to see a lot of you couldn't get the Bernoulli's equation right. It wasn't a very challenging equation. You just had to apply the Bernoulli's, right? The height, there was no elevation change. So you had the pressures, you had one velocity, you had to calculate the other velocity. So it was essentially a plug and chug. But there were some people who didn't even write down the Bernoulli's complete. So I understand where you're coming from, but I think that understanding which part of the lecture is important is also something that I need to teach you in this class. Does that make sense? Okay. So, yes, you want to say?
No, I was kind of gonna say, we're also kind of used to seeing not the questions being run out on the board. We're probably not used to seeing the questions being asked like in Word, I guess. We're kind of just doing the problem with the drawing and the free body diagram. You know what I'm saying? In classes.
I don't know what to do about that though. Like when you don't have a force balance, there's no way to draw a free body diagram, right? And most of the questions on this exam, we didn't have a force balance.
Well, I guess you're trying to say we're so used to working out with like pictures being drawn out already.
Okay.
Just figuring it that way.
Okay. We have one comment online. More practice problems. Okay, so as far as the pictures go, I don't know what to do because if a question doesn't have a picture, I cannot provide a picture for that. But if you let me put it this way. There are sometimes some people get confused reading the text of the problem. And that part you have to ask me. During the exam, doesn't really matter when it is. If you don't understand the problem, you can ask. There were a couple of people who did ask and got the answer. Okay, I didn't tell them the answer to the question, but I tried to remove the confusion, and it worked, right? They could answer the problem. Yes.
I think when you gave us the problems on paper that you were working out on the board, that was helpful too. Like sometimes you'll just do an example, and since we don't have like the question itself or like the drawing in
Okay.
class, when we take notes, it's harder to like go back and know what question that was for. So I think when you gave us the questions and said like, okay, now we're gonna work out 3.2, that was helpful because in our notes we have the question type with the solution
Okay.
rather than just notes of solution.
Okay. Okay. That makes okay. So what I'm going to do for that is to like upload a PDF file at the beginning of each chapter. Upload a PDF file of all of the examples that I think we are going to solve, so you can print it out and bring it to the class with you. So I think that's very easy to solve. Yeah, that's definitely what we can do. And if I forgot to do, because I teach, you saw my other student who came in. I teach 3 classes, so there are a lot on my mind. I may forget this. You please remind me. Send me an email or remind me in class. So, and we'll definitely try to work with you. And as far as the example problems, we got the online people to chime in. More example problems. I don't know about this. I think we have solved enough example problems. I'll try to solve more, but I don't know how much time we're going to have for more example problems. Okay. But I guess I will try to solve more. And like for this exam, we had one lecture in which the online lecture, I solved all of the homework problems, and I also one lecture dedicated to the exam, right? We solved, and after each chapter, we actually have one lecture dedicated to that chapter, and we solve the example problems. It's just too much material. I think we can cover everything if we do example. But I'll try to solve more example problems. Okay. Anyone else? I'm pretty sure there are, like, we don't have that many students in class. Most of you are online. But I'm pretty sure everyone here has something on their mind, right, that they think can help with their understanding of the class. You have to have some sort of an opinion, right? Yes.
Sort of on the same vein as like more example problems, I think a thing that might work that not like something that would work for me in my case is like other problems that aren't the homework that you just like have to, that sort of gives you an idea of what the test is going to look like.
Okay.
So like questions similar to the test, but not what's on the test and not the ones that you did for homework. There's something extra that you can sort of like test your knowledge against, see where you're lacking in understanding. So if you have an issue with this problem, you can go back and look over figure out.
Okay, that makes, I think we already did that though for this, because that all of the exam problems were either part of the homework or I solved something similar to that in class. But I definitely I can accept that. We can definitely work on that as well. Yeah, sure. Thanks. Anyone else? Nothing? Okay. So, and we don't have any comments from the online people. Any more comments? So this is what we're going to do. Or we have actually 2 options. So you were, in your opinions, you were mostly focused on the exam, but that wasn't my intention. I wanted to make sure that you guys are understanding the material, understanding the concepts, right? So if you have any opinions in that regard, please make sure to share that with us. But if you feel like that you are understanding the material, just have to need more practice, that's all right as well. And again, to be honest, I was planning to give you more complicated problems. then I toned it down. So from my perspective, it was a very easy exam. And I was really surprised to see that this many people couldn't figure out the questions, okay? So, like, because everything was very basic. You just had to know the Bernoullis, can solve the question. You just had to know how to deal with the shear stress. You could solve that. There's just one equation. It wasn't like you have to plug in a couple of equations, right? So yeah, I'm still a little, I don't know what happened there. But as far as the exam grade, the class average, I haven't calculated the average yet. I didn't like the grades that much, so I graded them and just put them aside. The class average is around like 60, 55, 60. So it is not a very good average. And I definitely expected a higher average, like around 80. Because I thought this was an easy exam. And what we are going to do, what we can do to improve your grades. I'm not going to curve the grades, as I've said. So what I can do is either to give you back the exam, you take it home, solve it for like 20 points, maximum 20 points, bring it back. Your grade will be whatever the grade is plus 20. Okay, that's one option. Right? Which again, since that average is so low, I don't think that would be very helpful. But the other thing we can do is actually there are one other option. The other thing we can do is to use the final exams grade for the exam one's grade. Okay, so essentially your final exam is going to be comprehensive. I'm going to single out the problems that are from chapter 1 to 3, and people who want to use that grade as their exam 1 grade, for those people, I'm going to like grade let's say 3 questions are from chapter 1 to 3 on your final exam. Those 3 questions will be graded. The grade of those 3 questions will be your exam 1 grade. Does this make sense? So we have 2 options. Instead of doing practice problems, students need a means to feedback. Back in chemistry. So we have one comment here that I'm not sure I understand. So maybe you guys in class can help me with this, because I didn't have the chemistry 111 and 112. So we have one person here, one of the students telling us that instead of just doing practice problems, the students need a means to give feedback. Back in chemistry 111 and 112, the students would use an online program that gave feedback and trials. LONCAPA is also good. I don't know what that is. So did you have any feedback system in your chemistry courses? I'm not sure what you mean, though. That's
basically what from my understanding is what he says. One chapter is the thing we use for homework, at least in the classes I use in my electrical stuff still. But basically what it does is it'll tell you when you're wrong, and you can sort of gauge where you need to figure stuff out from there. If you got a question wrong, it'll tell you that, and you sort of have to figure out where you went wrong and solve it from there. One of my other homework things tells you how to do the solution, but it makes you do it again. So if you get it wrong enough times, it will tell you how to do it, and it'll give you a new question, and then like you have to do it again.
Yeah, no, I understand that. I guess that's a very good idea, but I don't know how we can implement that in a like chemistry 111 or the general courses that you have taken with electrical are very huge courses, right? That's too much resources for this course that I'm the only one who's taking care of. But what I can do as far as the feedback, if you think giving you feedback is going to be helpful before submitting your homework, and there's actually one of your classmates who always comes to my office for the homework, right, Holden? Yeah, so he always comes to my office before the submission date and checks his solution, check his solution to answer to the homework problem. And we actually figure it out together. This is an option that is available to all of you if you want to. So if there's anyone in class who needs feedback on their homework, as I've said many, many times, you can always come to my office and get feedback on your solutions, right? If you think that would be helpful. But as far as like using a system to give you automatic feedback, I don't think I can implement that, at least at the middle of the semester. I definitely can't do that. Yeah. So what do you think about coming to the office and checking your homework? Is this helpful at all?
Yeah.
Okay. Yeah. So that's definitely something you guys can do. And okay, where were we? Exam. So this is how to treat exam 1 or how to help you improve your grade is going to be your choice. So whichever option that gets the most votes, essentially, we will go with that. Again, the options are either I give you back your exams, you will have like 2 or 3 days, 2 days. I'm going to give them back to you on Tuesday. You'll have to submit it by Thursday with all of the solutions to all of the problems, the correct solutions, of course, and you will get an extra 20 points, okay? Or we can solve the exam problems today instead of the whatever lecture we had planned, because like solving the exam problem is not a bad idea. And then I'm going to grade whatever problem I include from chapter 1 to 3 in your final exam separately. They will be part of your final exam grade anyways, right? But I'm going to grade them separately and use that grade as your exam 1 grade, whichever is the highest. So if your exam 1 grade is higher, then I'll just keep it as is. Which option do you want to go with? Who's going to vote for option 1? Show of hand. So, okay, that makes sense. Yeah, I'm sorry, I left the exams at home, and I don't have it in an Excel file. So I guess we can vote on it on Thursday. I think that's a good idea. Let's see, we have one question about getting our exam back to redo and get the correct answers. Okay. We're going to vote on it on Thursday. I'm going to give you your exam back, and you're going to have like 4 days to submit your answers on Tuesday, next Tuesday. And if you have everything correct, which I assume you will be able to get everything correct because the problems are not that complicated, you will get 20 points, 20 extra points. We will actually vote on it on Thursday. And if you have a comment, a feedback, or whatever that you don't want to share during the class, you can always send an email to me. Or if you think you need to meet with me, you please do so. Please make an appointment, come to my office. We can talk about whatever the problem you're having is. I saw a lot of stress when it came to this exam, and I didn't like it. I don't want you to be stressed about that. I mean, you will be stressed anyways. This is an exam, but I don't want you to be too much stressed about an exam. I want you to feel a little more comfortable. So, yeah, reach out. Any other questions or anything else? So I'm going to bring your, I will make sure to bring your graded exams on Monday. There are a couple of you who already know their grade because they stayed after the exam and I graded the exam for them. And for the rest of you, I will make sure to bring the exam grades on Thursday. What I'm going to do is I'm going to put the grades on Blackboard. Okay, so just expect a low grade because the average was very low, right? So don't be disappointed if you see your grade is very low. Okay. So let's continue. We So far, we have talked about chapter 4, fluid kinematics, and we talked about the total derivative or the substantial derivative. The idea was your acceleration of a fluid particle is the total derivative of velocity with respect to time. This total derivative has a local component, which is a term you are already familiar with, dv dt, or partial v, partial t, plus v del v, which in a Cartesian coordinate system, this will end up being partial u, partial u, partial u, partial u, partial x, v, partial y, and w, partial w, partial z. This is something we talked about. This part is called the convective term. And this part is called the local term. Okay? In an steady state type of flow, the local term is 0 because changes of velocity with respect to time is going to be 0. Hopefully you remember the example I gave you in class about the temperature, the changes in temperature. If we turn off the AC here, the temperature is going to change locally, right? I don't have to move for my body's temperature to change. That's the local term of the total derivative. But if I move outside, the outside temperature is changing. It's different from the inside temperature here, and that's the convective term. You don't see the board at all, do you? I try not to write down here. Yeah. Yes.
What is that, convective?
Convective, yeah. It's called the convective term.
All the terms top and bottom one equation.
Pardon me?
Is the top and bottom one equation?
So this part is the convective term, and this is the expansion of the convective term. Yeah. Okay, this is something we have seen 2 weeks ago, right? And you can actually apply the total derivative analysis to anything, right? It's not just acceleration or velocity. If you take the total derivative of temperature, you will have, that's essentially the example I gave you, the changes of local changes of temperature plus the convective changes of temperature. And this equation applies to a Cartesian coordinate system. Okay. Again, this part is an expansion of v del t. Again, you can take the total derivative of any parameter. It doesn't have to be velocity or to give you the acceleration. But if you take the total derivative of acceleration, it will give you a total derivative of velocity. It will give you the acceleration of a specific fluid particle. Okay, so let's have an example. We are given this. I will make sure to send you the text of the example problems from next lecture. But let's say we are given this velocity field, u of x I. So it's a one-dimensional flow field, which this u of x is equals to v naught 1 plus r cubed divided by x squared, x cubed r. And this is a velocity field of a flow of a specific streamline on the flow over a cylinder. This is the velocity field of this specific streamline, point A to B. We want to find the acceleration of this velocity field. So acceleration, total derivative of velocity with respect to time. We give you the acceleration. Write the equation, partial v, partial t. See this velocity component is not a function of time. So which tells you that we are in a steady state situation. So this part is 0 plus u partial x plus v partial y plus w partial z. It's a one-dimensional flow field, so v and u are 0, which essentially means that their derivative is going to be 0 as well. The only component of velocity present is u, and it is also a function of x. So your acceleration is going to end up being u du dx. Okay. Okay. What is the velocity component we have there? U of x, that's the component of velocity in the x direction, is v naught plus 1 plus r cubed over x cubed, right? And so that one is present in the acceleration formula that we have here. But we also have to take the derivative of that velocity component with respect to x. What is the derivative of this velocity component with respect to x? Who can tell me what the derivative is? I'm going to take the derivative of this velocity with respect to x. Any idea? This actually taking this type of derivative was part of the exam. And a lot of people couldn't take this derivative for some reason. That's why I'm stopping here for a little bit. So, anyone? Is there anyone who can tell me how we can take this derivative? That's the derivative of u with respect to x, and we have a v naught, which is a constant. Think of it as 2, 1, whatever. 1 plus r cubed divided by x cubed. We can actually multiply everything by the v naught to make it even simpler. V naught plus v naught r cubed divided by x cubed. We can divide it to two derivatives. V naught r cubed x cubed. V naught and r cubed are constant, so we can take them out of the derivative. And v naught r cubed. Take it out of the derivative. So, what is the derivative of a number with respect to x? 0, right? Exactly. What is the derivative of 1 over x cubed with respect to x? How would you take that derivative? How would you take the derivative of a polynomial in general? You have to speak up. -3. So what was your name again? Mary Jane, yeah. -3 divided by x to the power 4, right? So essentially, you have to, this is x to the power -3, right? You have to subtract that power by 1, is -3 minus 1 is -4, and then multiply your polynomial by your power. Okay. So this is an example of how to take the acceleration for with using the total derivative. And if you were told to find the acceleration at a specific point, you just have to plug in the value of x at that point. You will be given the value of x, of course, like at x equals to 1, whatever. You can find the value of acceleration, the magnitude of acceleration at that specific point. Okay. So we have one more tool, if you will, that we need to talk about. And then we can go to talk about the meat of this coordinates, meat of this chapter. And that tool is the streamline coordinates, or a streamlined coordinate system. At this point, you are already familiar, hopefully, you're already familiar with the Cartesian coordinate system, x, y, z, right? And the unit vectors are I, j, k, right? And cylindrical coordinate system are theta, z. And also the spherical coordinate system, theta, phi, r, theta, phi, right? We are going to introduce a new coordinate system, which actually we have seen in this class before, but we haven't talked about it specifically. A streamline coordinate system is a coordinate system that sits on your streamline and moves with the streamline. So if you have a streamline like this, your coordinate system it's a two-dimensional coordinate system because of the nature of the streamline. And we'll always have one axis tangent to the streamline, which we are going to call S, and one axis normal to the streamline, which we are going to call N. Right? And as I said, that coordinate system can move depending on the position you're looking at, depending on the time, and a lot of things. But the only thing that is going to be fixed about this coordinate system is the fact that it sits on the streamline. Okay. But if you recall, we defined the streamline as a line that is always tangent to velocity. Okay? So your streamline is always tangent to the velocity. What does it mean for the velocity? Let's say I want to present my velocity using this coordinate system instead of the regular Cartesian. In Cartesian, your velocity was ui, vj, wk, right? The most general type, 3 different directions. It could have 3 different components on all of the axes. But how can I present my velocity in this streamline coordinate system? You always have to keep this in mind, that the definition of a streamline is that it is always tangent to the velocity. So based on this definition, how can I represent my velocity vector using this coordinate system? Okay. Does it have any component in the n direction? No. Why not? Because of the definition, right? We define the streamline as a line that is tangent to velocity. So that's actually the good thing about this coordinate system, that your velocity does always only have one component in the s direction. Let's say s hat is the unit vector in the s direction. So instead of like I or j or k, we are going to have the unit vectors are going to be s hat and n hat. So your velocity is going to be v s hat and 0 n hat, right? And it's a two-dimensional case. Okay. What about the acceleration? We have talked about the acceleration part when we were deriving the Bernoulli's equation. On a streamline, the acceleration will have two components, can have two components, one in the s direction and one in the normal direction. Okay. So the good thing about the streamline coordinate system is that your velocity will always be a one-dimensional velocity. Okay? So let's find the acceleration using the total derivative formula. And instead of using the Cartesian coordinate system, we are going to use the streamline coordinate system. What would be the difference here? So in Cartesian coordinate system, your total derivative was partial v partial t plus u partial x v partial y w partial z. And this was in Cartesian coordinate system, right? X, y, z. I want to write the same equation, but only this time I want to use the streamline coordinate system. The changes of velocity with respect to time is going to stay the same. So we're going to get partial v partial t. But for the rest of it, we are only going to get v, that's the velocity in the s direction, partial v partial s, right? And the rest of it is going to be 0 partial velocity, partial 0 partial n, right, which essentially is 0. So this will be the representation of acceleration using the total derivative formulations. Okay? But eventually, I'm not going to go through the derivations here to give you the acceleration. And the derivations are going to be there on the lecture notes, which I'm going to upload today, if I haven't uploaded already. Okay? But eventually, what you are going to get for acceleration, if you do the calculation, is going to be this. Acceleration is going to be equals to v dv ds I plus your centrifugal acceleration in the normal direction. V squared divided by r, not in the I direction, in the s, in the n direction. Okay. This is something we saw in chapter 3 as well. But if you use the, again, the idea is if you use the streamline coordinate system, this will be your acceleration, and your velocity will always be tangent to the streamline. So you will only have one-dimensional velocity. Any questions so far? No? Have we heard about the centrifugal acceleration at all? Centrifugal acceleration. Have you heard about this in dynamics, or I assume in dynamics? Not yet. Okay. I mean, you will definitely see this, and but the derivation is there in fluid mechanics in the lecture notes. If you wanted me to do the derivation, you can always come to my office. We'll go over the derivation. So we have learned about the total derivative. We have learned about the path lines, streak lines, and streamlines in like 2 weeks ago, a long time ago. And we understand the streamline coordinate systems. There is one more thing that we need to understand before learning about the main governing equation of the fluid mechanics equilibrium, control volume and systems. Okay. In fluid mechanics, any kind of a closed surface is called a system. And what do I mean by a closed surface? This essentially means that there is no mass going in and going out, right? So we have some fluid inside this spray, a spray can, right? If I don't push this, there won't be any mass going out and going in. It doesn't really matter what I do with this, right? This is a system, an example of the system, okay? But if, and the system itself can, like, it can change shape. Like this system, you can like push it or pull it or whatever. You can change shape. The only criteria here is that a system cannot lose any weight. It won't be able, it won't lose any weight. But on the other hand, we have another concept called a control volume. And a control volume is a fixed volume. So it can use, it can change shape. It can move with just translational velocity. We'll talk about that as well. And there will be mass going in and going out of this control volume as well. This is all called a control volume. I assume you have seen these concepts in your thermodynamics as well, but I just had to reintroduce them to make sure we are on the same page when we talk about this. So then the next question is, let's say we have all the tools. At this point, we have all the tools we need to understand the governing equations of fluid mechanics, the main equations of the fluid mechanics. And this main equation or main tool is called is derived from a theory called the Reynolds transport theorem. This Reynolds transport theorem essentially gives you a way to find the changes of any property with respect to time. That's the idea. It gives you a theory to find that. And conceptually, it's a very understandable concept, right? This is something that you can definitely understand. Okay, let's think about it this way. Let's say we have this type of geometry, okay, and we have a control volume inside of it. And at the same time, we have a system on top of the control volume. So at time 0, let's say, the system and control volume are the same. But when the time passes, at time t1, your control volume is going to stay put, but your system is going to move. And we want to find the changes in this property B inside that control volume over this time period. So dB dt over 0 to T1, right? Inside the control volume. So inside this, a small area. How do you think we can find this change? How has the mass changed? Think about it. I'm going to need you to give me an answer. How do you think this property B has changed with respect to time inside this control volume, which is the orange chalk? And let's name these regions. This is region 1. This is region 2. And the control volume is going to be the orange region. Just based on this, how much of this B has moved out of this control volume? This much, right? During this time T1, this much has moved out of the control volume. Is this correct? How much of new B, whatever that parameter is, like the mass of oil, whatever, how much of this new B has moved into the control volume during this time T to T1? Section 1. And the original mass of the system was the mass of this system, right? So mass of the system, amount of B in the system minus the B of part 2 plus the B of part 1. Okay? That's the amount of mass that has. That should be the amount of mass. But all of this has to be added by the amount of local changes. Right? The B itself can change inside the control volume. Think of B as your temperature, right? Let's say a hot temperature, a hot fluid is coming in, and you have this expansion happening here. So the temperature is going to change when it's going out of the control volume. That will account for zone 2 coming in. Whatever hot fluid is coming in, that will account for zone 1. And let's say you have some cooling happening around it. That will account for the changes of B, changes of temperature inside that control volume during that time, right? That doesn't have anything to do with the thing going out or coming in. Okay? Does this make sense? So your Reynolds transport theorem is going to give you the total change of that parameter B with respect to time inside the control volume. So it is essentially going to relate the changes of B during time inside the control volume to the movement of the system out of that control volume. Does this make sense? Okay. So one thing I think I forgot to mention, yes I did, is the two types of properties we have here. And this is something you have to make sure that you have to keep in mind. We have capital properties, whatever that property is. If it's mass, capital M. If it's velocity, capital V. And these are called the extensive properties. These are thermodynamic properties. Extensive properties. We also have this small letter properties. These are called intensive properties. Extensive properties are the regular property, and intensive property are that property divided by mass. For example, if your extensive property is mass, your intensive mass is going to be mass divided by mass 1. Okay? If your extensive property is MV, your intensive property is going to be only V, okay, divided by M. If your extensive property is 1/2 mV squared, your intensive property is going to be 1/2 V squared, okay? Whatever property you have, whatever extensive property you have, you are going to divide it by an M to get the extensive properties. So, and let's actually have the general form of Reynolds transport property. We have the derivation in the lecture notes, but I don't want to do the derivations. I want to give you the final equation, and we can talk about the equation itself instead of going over the derivation, to make sure that you understand the equation. So the rate of change of an arbitrary property, whatever property that is, dB dt, is going to be equal to the local changes of that property, partial t. And we will talk about this part in a second. Rho b d dv. I'm going to explain this in a second. Just give me 1 second. And control surface, rho v, v and dA. Okay. So, yeah. Let's try to understand this problem. So total changes of B in your system with respect to time is going to be equal to the local changes of B. Okay. But how is this local changes of B? This was your intensive property, right? Intensive B, whatever that is, right? The extensive of it was your capital extensive, was your capital B, right? This B is being multiplied by the integral of rho dV. Okay, I'm just assuming that it doesn't change its volume to make the concept a little easier to understand. Okay, what does the integral of rho dV give us? Calculate for us. That's rho multiplied by volume. If you assume rho doesn't change with locations, with volume, that's rho multiplied by volume. What is rho multiplied by volume? Density multiplied by volume. What is it? Mass. Okay. So this part is going to give us your intensive property multiplied by mass, which is the extensive property. So the first part of the Reynolds transport theorem is calculating the changes of the local changes of that extensive property for us, right? If you recall, we had the total derivative, was the local derivative, partial t, plus the rest of it, right? But this part, so this part is calculating the flux of that property B outside and inside of your volume. So this part is actually the mass in or mass out of, I mean, if it's mass in or mass out, the influx and outflux of that property. If you're talking about temperature, that's hot fluid coming in, cold fluid going out. Yeah, that's what it is. I forgot a B here. Okay? That's essentially the flow rate of that. This integral will calculate the flow rate of that a specific property for you out of the system or inside the system. So eventually the concept, as I said, is not that hard to grasp. The changes of a specific extensive property in a system is going to be the local changes inside that control volume, inside the system, right? Meaning that, let's say you're dealing with temperature again. Let's say you're heating up or you're cooling down, whatever you have here, and plus the net flux of it. The difference between what has gone out of the system minus what has come in the system, right? That will give you the total changes of a property in a system. Does this make sense? Again, let's deal with temperature. Let's say we don't really deal with, we have to deal with energy. But this is just so you understand it better. Let's say I'm applying like 300 Kelvin, 400 Kelvin at this side. Temperature is coming in with 350. We are not going to do any calculations. So this is just concept. And temperature is going up with 380. Right, and here in the middle, we actually want to find the changes of temperature with respect to time. Changes of temperature with respect to time, we can separate it to two different forms. One is by removing this going out and coming in parts. The changes of temperature with respect to these local changes with respect to this heating, right? This will be accounted for by this part of the equation. And then you remove the heating. You just account for the fluid coming in with a specific temperature of 350, right? And fluid going out. That will be taken care of with this part of the problem. Okay. I mean, at the end of the day, I can't think of a situation that you need to take these integrals, right? As long as you understand the concept, you should be good to go, okay? Should be fine. So, again, let's actually write this equation for mass. Let's see what it's going to give us. This extensive property, M, intensive property, 1. Okay? So we want to find dm divided by dt. Is going to be equal to partial t of integral over the control volume of rho. What is b here? B is 1. We are dealing with mass. Rho dv plus the integral of rho v vn b is 1, right? Integral of rho dv is going to give you the mass. So local changes of mass again plus the integral of rho v squared dA. What is rho v squared dA? That's how we define mass in and mass out. So if in the Reynolds transport equation, if you plug in m, you're going to get the changes of m with respect to time is the temporal changes of m, mass, plus m dot in minus m dot out. So this will give you the, and this is 0 for mass, right? So you're going to get the conservation of mass equation, okay? Do you have any questions? What time is it? Do we understand the topic here? So what we're going to do for the next lecture, that's essentially that's it for chapter 4. That's chapter 4. As long as you see this Reynolds transfer theorem and you understand what it does, that's chapter 4 for you. And then in the next lecture, where we start chapter 5, what we're going to do is we are going to use different extensive properties, and these three specifically, and come up with the governing equations for the fluid mechanics, the main governing equations. And you will see more application of this specific Reynolds transport theorem right there, and you will see the essentially the results of using this Reynolds transport theorem. But before moving on, let me ask you one question. What do we call this property? It's the momentum, exactly. So what about this one? Energy, exactly. Kinetic energy, to be more precise. Okay, so if for this B, for this extensive property, you plug in this mv, you will find the momentum equation. And I think we have used this term before in this class, momentum equation. And the momentum equation is the equation we use to find the Bernoullis, right? That's the force balance eventually. And if you plug in energy here for the extensive property, you will get the energy equation, which is an equation you will definitely work with in your heat transfer class next semester. No one has taken heat transfer class in this. Yeah. Hopefully in the spring or the summer, or in the fall or the summer. Okay. Let's see. We have one comment here. Let's see. Mass momentum. Yep. Has increased. Yeah, we had a couple of comments online, but I can't get to your comments in time. Okay, there is one thing that your control volume can also be moving, but so far we are going to assume that the control volume is going to be only moving, can only translate, right? It doesn't rotate, it doesn't anything, it doesn't do anything else. It can only translate, which essentially means that your velocity, you're going to get a relative velocity, which is your absolute fluid velocity minus, let's call it VREL, relative velocity, or absolute fluid velocity minus the contour volume velocity, whatever that is. So contour volume CV velocity. The problems that involve a moving contour volume are a little more complex, but we will definitely solve an example of this as well. And this is your absolute velocity, and this is your relative velocity. We will definitely solve an example of this as well. And let's actually think about this. Is there anyone who can give me an example of a moving control volume? Rocket nozzle. Okay, that is a depending on your frame of reference, a rocket nozzle is a moving control volume, exactly. If your rocket is working correctly, right? Is working as it's supposed to do. So you have in a rocket nozzle, we usually have a convergent divergent nozzle. Let's say this is your control volume, very badly drawn. Converging. Let's say this is your control volume. The idea is this is moving at some speed, right? To either go to the I guess a space or to hit somewhere. But this is moving with a velocity, right? And the fluid inside of it is also coming in and going out. Okay, the fluid inside of it is moving at a speed v whatever, right? And the rocket itself is moving at another speed. So the relative velocity of this fluid is going to be the subtraction of these two. That was a very good example. Thank you. That was a very real world example. But your book has your book's example is actually not a very good example. So I don't see how would anyone use this application. And so they have this a water jet that is pushing a stroller back. So I don't see how anyone would push a stroller back with a water jet. And they are using the stroller as a control volume. Any questions? Okay, so that is it for chapter 4 of the book. It is a short chapter. Conceptually, it's a little harder to grasp. I understand that. But as long as you understand the streamline coordinates and as long as you understand the total derivative, you should be fine. And we will solve some example problems. We will actually use these extensive properties and find the governing equations for the fluid flow in the next lectures. And then we'll solve some example problems. Make sure to join the class or either online or come to class face-to-face to be able to vote for your whatever desired outcome is of the election we are going to hold on Thursday. I'm planning to post your grades tonight. If your grades was too low, don't be discouraged. You still have the option. Even if, let's say your grade is 0, which we don't have anyone with a grade 0, but let's say even if your grade is 0, you still have the option of getting an A, right? But on the other hand, you have to be thinking realistically as well, right? So if you don't understand anything about this class, you make sure you have to talk to me, right? So nothing's going to change in the second half if you don't understand anything about this class. But if you feel comfortable with the concepts, I'm pretty sure this exam, if you have done bad on this exam, I'm pretty sure this exam was a fluke and you can recover. And we are not going to punish you for a fluke. Yes?
So it's going to be a class consensus of, like, it's all or nothing, so everyone has to do the same method?
Yes, everyone. So whichever method gets the most votes, we'll go with that. We definitely cannot have a unanimous consensus here. I mean, not everyone is going to agree to one option, but whichever option.
Individuals, you can't choose what you want to do.
I'm leaning towards not doing that, but yes.
They could leave the 3 problems for the final as an option for a student to want to solve them and get a better grade.
You have to solve those three problems anyway. Those will be part of the final exam, right? So because the final exam is comprehensive. So I just gave 3 problems out of nowhere. There may be 4, there may be 2, there may be whatever, right? But you have to solve those anyways. There's no other way around it. And I don't want to give out like 15 problems and tell you to solve like 12 of them and solve 3 for exam 1. That's a lot of work for you guys, okay? So at this point, I'm leaning towards not giving individual people the freedom of choosing, right? But we'll see what happens. If we were 50-50, then I will give you freedom to choose whatever. Okay. Yeah, fire hose as well. And that's a little too late for that example. So that's it. That's it for today's class. What time is it? 4 or 5. We are done with the class anyways. And see you on Thursday.